The winter wind cut different along the upper Mississippi in 1842 when Hans Eriksen watched blue smoke roll across his cabin ceiling and felt ice form on his water bucket just 3 feet from a roaring fire. He had built his chimney exactly the way every settler in the Minnesota Territory was told to build it. Deep stone firebox wide as a man's outstretched arms, rough field stone stack, and a flue big enough to let the fire breathe. By February, he had burned through 4 cords of wood where 2 should have lasted, and still his family huddled in smoky corners, while bitter drafts scoured the floor. Across the frontier, Norwegian and Yankee families alike were losing the same battle in cabins built by the book and failing by the season. Over the next 3 winters, Hans quietly combined techniques, borrowed from old-world stovecraft and indigenous airflow wisdom to build a chimney that used 1/3 less wood, kept smoke out during blizzards, and threw steady heat into rooms that stayed warm enough to keep water from freezing. When the brutal winter of 1857 locked the territory in months of deep cold and cutting wind, his impossible, narrow-throated design kept families comfortable while neighbors' standard chimneys filled their homes with smoke and ate through wood piles by January. Today, I'll break down the exact measurements, the forgotten ratios, and the simple principles that made this settler's hybrid chimney system outperform everything else on the frontier. What did Hans understand about the path of smoke and heat that every other builder in the territory had missed? The accepted method across the Minnesota Territory followed patterns borrowed from older American frontiers and army installations. Settlers built their chimneys of loose fieldstone pulled from creek beds, stacked with mud mortar on the gable end of their cabins. The firebox stretched as wide as a man could reach with outstretched arms and nearly as deep, based on the reasoning that bigger meant safer and more heat. The flue rose straight up through rough stones, wide enough for a child to climb, with no narrowing at the throat and no intentional ledge to catch downdrafts. Men trusted this design because they had seen it work at trading posts and military quarters, and because the bigger is safer thinking seemed to guarantee good draft while keeping sparks away from the log roof. Hans Eriksen had grown up in a Norwegian valley where winters stretched long, and wood was precious enough that wasting fuel was considered a moral failing. As a boy, he had carried brick and mixed clay for Niels Johansen, an older stove mason who specialized in tiled masonry heaters that could warm a house through the night with one good firing. From Johansen, Hans learned that hot, smooth flues drew cleanly while cold, rough chimneys sulked, and that openings must match the size of the fire rather than fight it. He had also studied crude diagrams in religious pamphlets that Pastor Anders Lund carried from Europe, showing tall, narrow fireboxes with shaped throats that were already accepted among educated builders overseas. The contrast between what Hans knew and what he saw in the territory was stark. His neighbors' chimneys broke nearly every rule Johansen had drilled into him. The flues ran far wider than needed for the firebox opening, creating cold pockets where smoke could eddy and roll back. The thick outside stacks stood exposed to wind and weather, chilling the smoke column and weakening the draft on cold days. Most critically, the fireboxes sat deep in the wall like stone caves, sending the flames heat straight up the throat instead of radiating it into the room where families needed it. Hans watched these failures play out in cabin after cabin during his first winter in the territory. When north winds shifted the air pressure, neighbor families faced an impossible choice between freezing with doors cracked open or choking with them shut. The Hartwell cabin filled with blue smoke every time snow loaded the roof and changed the chimney's draw, forcing Martha Hartwell to keep her youngest child outside in below-freezing air just so the baby could breathe clearly. Old Henrik Torsen's chimney leaked smoke into the log, chinking during a January thaw, nearly setting his roof alight before neighbors could drag the burning logs out into the snow with iron hooks. The health toll mounted through the winter months. Children developed harsh coughs that lingered for weeks, their lungs irritated by smoke that hung at head height whenever the wind swung wrong. Elders complained of burning eyes and headaches that seemed to worsen on the windiest days, when chimneys drew poorly and rafters blackened with soot. Hans noticed that families spent more time outside their own cabins than seemed reasonable, even in bitter cold, simply because the air inside had become unbreathable. These visible disasters connected directly to what Hans remembered from his boyhood training. Johansen had warned that wide, cold chimneys would always smoke unless overfired, wasting precious fuel without delivering warmth to the people who needed it. The stove mason had built his reputation on heaters that used narrow passages and warmed masonry to stretch each armload of wood through long northern nights. Heat lost up an oversized flue, Johansen insisted, could never warm children or dry boots. Hans began his own quiet experiments that first winter, but cautiously. He laid out his cabin hearth with a smaller opening than local custom demanded, and made the firebox somewhat shallower than his neighbors built theirs. Using a shaped timber form to guide his stones, he attempted a modest narrowing just above the firebox, creating what he hoped would function like the throat constrictions he remembered from Norwegian designs. The improvement was measurable but incomplete. His cabin stayed less smoky than others, but the draft still turned touchy when certain winds hit the roof, and he noted these failures with the same careful attention he paid to successes. The social resistance came almost immediately. Elias Hart and other Yankee farmers saw Hans's smaller, more enclosed hearth as evidence of old country stinginess. They insisted that a chimney needed to breathe and that tight masonry would choke the fire, pointing to the wide, simple builds at the fort and trading post as proof that American methods worked. When Hans suggested that the cookhouse chimney at Peterson's logging camp might draw better with a narrower throat, the foreman dismissed him outright, claiming that army patterns and established frontier practice trumped foreign fussiness. The skepticism cut deeper when neighbors accused Hans of bringing unnecessary complications into a country where speed mattered more than craft. They argued that tight construction and narrow passages belonged in settled country with plenty of skilled masons, not on a frontier where families needed shelter fast and reliable. Some suggested that Hans's approach might work for a single man's cabin, but would never handle the cooking and heating demands of a real household with children and winter chores. Hans faced a choice that would define the next several years of his life in the territory. He could accept that frontier conditions demanded frontier solutions, even if those solutions wasted fuel and filled lungs with smoke. Or he could trust the knowledge he carried from Norway and the evidence of his own eyes, developing a complete hearth and chimney system that combined traditional proportions with materials and methods that ordinary settlers could manage. The path forward required not just one clever adjustment, but a systematic approach to firebox geometry, throat design, air supply, and structural details that could survive frontier conditions while delivering the clean heat and efficient burn that proper masonry had always promised. Hans committed to rebuilding his hearth system entirely during the spring of 1843, focusing first on capturing and redirecting the heat that standard fireboxes sent straight up the chimney. The fundamental problem lay in geometry. Deep, boxy fireplaces placed the flame far back under a straight stone lintel, so most radiant heat traveled directly into the throat rather than radiating outward into the room. Wide fireboxes encouraged oversized fires that blasted heat up the flue, while people sitting to the sides still felt cold air against their backs. Hans calculated that his neighbors burned through 3 full cords of wood each winter and still woke to frost forming on the inside surface of their log walls. The solution required borrowing techniques from the shallow, high-fire openings Hans had studied in European pamphlets and adapting them to frontier fieldstone construction. He rebuilt his firebox to measure only 1 foot deep from front to back, roughly 3 feet wide and 2.5 feet high. Most critically, he angled the back wall forward toward the room above the fuel bed, using a wooden form to guide the stones into the proper slope. He splayed the side walls outward so that flame and glowing coals remained visible from most positions in the room, dramatically increasing the surface area that could receive direct radiant heat. The throat modification required precise measurement to achieve the dramatic efficiency gains Hans sought. Just above the firebox opening, he constricted the passage to a narrow slot only a few inches high before allowing it to widen again into the main flue. Hans shaped this throat opening to roughly 1/10, the area of the firebox opening, using a wooden template he carved specifically to check the proportions. The narrowed passage created a venturi effect that accelerated the hot gases upward, generating strong draft even with smaller fires, while preventing the volume of heated room air that typically got sucked up wide, uncontrolled flues. Behind the firebox, Hans built substantial thermal mass that fundamentally changed how his hearth delivered heat over time. Instead of the thin back wall typical in frontier construction, he created a masonry core nearly 1.5 feet thick, tying it into a chimney mast that rose through the cabin's interior rather than standing exposed on the outside wall. This thermal battery absorbed heat during active burning and continued radiating gentle warmth for hours after the flames died, smoothing out temperature swings and reducing the number of firings needed each day. The knowledge for these innovations came from multiple sources Hans carefully synthesized. Niels Johansen had taught him that masonry heaters in Norway used heavy stone or brick masses as heat storage systems, absorbing the intense heat from fast, hot burns and releasing it slowly over 12 to 16-hour cycles. The European pamphlets Pastor Lund shared contained diagrams showing how angled firebacks reflected radiant energy toward room occupants instead of allowing it to be absorbed and lost in the throat area. Hans combined these principles with his own observations of how heat moved through his cabin during different weather conditions. The first full winter test came during 1843 to 1844, when repeated cold snaps locked the upper Mississippi in ice for weeks at a time. Hans measured his results against the performance of neighboring cabins built to standard frontier patterns. In Elias Hart's deep box fireplace cabin, water left in a pail near the far wall froze solid most winter mornings, and the family required 3 or 4 heavy firings each day just to maintain survivable temperatures in the main room. Hans's redesigned hearth kept the same volume of space consistently warmer with only 2 substantial firings per day, maintaining interior temperatures near 50 degrees Fahrenheit even during the coldest periods. The fuel savings proved dramatic and measurable. Hans carefully tracked his wood consumption against his previous winter's usage and against estimates from neighboring families of similar size. His angled firebox and thermal mass system reduced his winter fuel needs to approximately 2 cords where he had previously burned 3, and where families like the Harts consumed 3.5 cords or more. The difference represented several fewer days of dangerous winter cutting and hauling, allowing Hans to focus on equipment maintenance and indoor projects during the harshest weather. The thermal performance gains challenged conventional frontier assumptions about fireplace design. Neighbors insisted that only a deep, wide fireplace with tall, roaring fires could heat a drafty cabin effectively, arguing that any attempt to cramp the opening would result in smoke and weak heat output. Hans's measured results proved that geometry controlled heat delivery more than raw fire size. His narrower, shallow hearth threw noticeable radiant warmth across most of his cabin's single room while consuming substantially less fuel, and accomplished this without the constant smoke rollouts that plagued standard builds. The success prompted Hans to refine his system further and document the specific ratios that produced optimal results. He carved permanent gauge sticks marking the critical relationships between firebox width, height, depth, and throat opening that could be applied to cabins of different sizes. The firebox interior dimensions of 3 feet wide, 2.5 feet high, and 1 foot deep became his standard proportions for typical single-room frontier cabins. The throat area, measuring 1/10 of the fireplace opening area, provided reliable draft without excessive heat loss. The thermal mass extending 18 inches behind the firebox offered sufficient heat storage without requiring excessive stone and labor. Hans recognized that his thermal improvements represented only part of the complete system needed for reliable frontier heating. While his angled firebox and thermal mass delivered heat more efficiently, certain wind conditions still occasionally pushed smoke back into the room when the fire burned low. The air supply entering his cabin remained uncontrolled, sometimes creating drafts that swept heat away from people, and sometimes failing to provide adequate combustion air when doors and windows were tightly closed during storms. The next phase of his system would need to address these airflow challenges while preserving the thermal gains he had already achieved. During the winter of 1844 to 1845, Hans discovered that his thermal improvements had created new challenges with air management that required systematic solutions. Strong north winds could still drive smoke back through his narrowed throat when the fire burned low, and his tightly built cabin sometimes starved the flames of adequate combustion air during sealed-up blizzards. The problem lay in uncontrolled air movement. His fireplace still drew combustion air from random cracks throughout the cabin, creating cold drafts that swept across floors and pulled heated indoor air up the chimney along with the smoke. Hans addressed the combustion air issue by installing a dedicated outside air intake positioned strategically near the hearth. He drilled a 4-inch opening through the log sill approximately 1 foot from the firebox, lining it with a short clay sleeve to prevent air leakage around the edges. The intake delivered cold outside air directly to the fire rather than forcing the flames to compete with room air for oxygen. He fitted a simple wooden slide cover that allowed him to throttle the air supply when the fire was banked or completely out, preventing unnecessary cold air infiltration during non-burning periods. The smoke shelf modification required rebuilding the masonry immediately above his throat to create a horizontal ledge that would intercept downdrafts before they could spill into the room. Hans constructed this shelf by extending the back wall of the flue forward roughly 6 inches, creating a pocket where descending cold air would be forced to curl and mix with the rising column of hot gases. The shelf depth measured approximately 1/3 the width of the throat opening, providing sufficient area to catch and redirect downward air currents without restricting the upward flow of smoke and combustion gases. Hans extended his chimney height significantly above the roof ridge to create a taller column of warm air that would draw more consistently during variable wind conditions. He added 3 feet of additional height to his existing stack, bringing the total chimney elevation to approximately 6 feet above the roof peak. At the top, he shaped a simple stone cap with sloped surfaces that deflected wind upward rather than allowing gusts to strike directly across the flue opening. The cap design encouraged airflow to accelerate over the chimney top, creating a low-pressure zone that assisted the natural draft. The knowledge for these airflow innovations came from direct observation of indigenous building techniques and consultation with traveling European craftsmen. During trading visits to Dakota villages along the Minnesota River, Hans was invited into earth lodges where he studied how central fires functioned under smoke openings positioned at the dome's highest point. A Dakota elder explained that their rounded roofs encouraged wind to slide upward, creating suction that drew smoke cleanly, while low entrances prevented cold drafts from disturbing sleepers around the fire. Hans recognized the same principles he needed, controlled low air intake and protected high exhaust. A German stonemason named Johann Bauer, contracted to build the mission chimney at Traverse des Sioux, demonstrated European methods for running dedicated air ducts under hearths to supply combustion air without chilling living spaces. Bauer showed Hans how German stove fitters routinely connected outside air directly to the firebox through channels built into the foundation, preventing room air from being consumed by the fire. This confirmed Hans's approach of separating combustion air from the heated air that families needed to breathe and stay warm. The complete system faced its crucial test during a severe blizzard in February of 1846 that lasted 4 consecutive days. Wind-driven snow-sealed doors and windows, while temperatures dropped well below 0 degrees Fahrenheit. In cabins with conventional wide chimneys, families were forced to crack doors or windows periodically to prevent smoke accumulation, allowing snow to blow inside and covering floors with ice that further chilled the interior. The Hart family endured repeated smoke incidents that forced them to choose between suffocating indoors or freezing with openings to the storm. Hans's integrated air management system performed dramatically better during the prolonged storm. The dedicated outside air intake supplied adequate combustion air, even with every door and window sealed completely shut. The smoke shelf intercepted the occasional downdrafts caused by shifting wind directions, preventing smoke from rolling into the room for more than a few seconds at a time. The extended chimney height and shaped cap maintained steady draft despite the chaotic wind patterns swirling around the cabin during the blizzard. The measured improvements in indoor air quality were substantial and immediately noticeable. Families in Hans-modified cabins could keep all openings closed for hours at a time without smoke accumulation, while standard chimneys required door or window cracking every 15 to 20 minutes during windy conditions. The dedicated air supply reduced floor-level drafts significantly, allowing people to sit comfortably against walls without cold currents flowing around their legs. Children and elderly family members reported fewer respiratory problems and less eye irritation compared to previous winters in smoky cabins. The success of Hans's airflow system challenged deeply held frontier beliefs about cabin ventilation. Neighbors had long insisted that smoky rafters proved the chimney was breathing properly and drying the cabin, while tight construction would cause fires to smother from lack of air. Hans's results demonstrated that controlled ventilation through the chimney system could maintain adequate air exchange without wasting heat or creating uncomfortable drafts. His cabins showed clean rafters and comfortable air while still providing sufficient fresh air circulation. The air intake dimensions became standardized through Hans's continued experimentation with different cabin sizes and chimney configurations. The 4-inch outside air opening proved adequate for typical single-room cabins with moderate-sized fires, while larger spaces required proportionally bigger intakes. The smoke shelf depth of roughly 6 inches worked effectively with throat openings of various widths, providing consistent downdraft protection. The chimney extension of 3 feet above the roof ridge became Hans's minimum standard, with taller extensions recommended for cabins in particularly windy locations. Hans documented his complete ventilation system using the same gauge stick method he had developed for Firebox proportions, creating templates that allowed other settlers to reproduce the critical dimensions. The outside air intake positioned within 1 foot of the hearth, the smoke shelf extending 1/3 the throat width, and the chimney height reaching at least 3 feet above the roof ridge became repeatable standards that ordinary families could implement with basic tools and materials. The system now controlled both heat delivery and air movement, but Hans recognized that structural durability would determine whether these innovations could survive the harsh freeze-thaw cycles that destroyed so many frontier chimneys within a few years of construction. Hans recognized by 1846 that his thermal and airflow innovations would fail without proper structural foundations that could withstand the brutal freeze-thaw cycles that destroyed most frontier chimneys within 5 to 7 years. Across the territory, he observed chimneys built on shallow rubble footings cracking and tilting as frost penetrated the ground, creating gaps between masonry and cabin walls where sparks could ignite chinking and log ends. The Anderson family lost their entire cabin when hot gases leaked through separated joints and set the roof ablaze during a January cold snap, forcing them to sleep in their barn while rebuilding in sub-zero temperatures. The foundation solution required digging below the frost penetration line that extended roughly 3 feet deep in Minnesota soil. Hans excavated his chimney base in a carefully shaped pit that measured 4 feet deep and flared the footing 18 inches wider than the chimney on all sides. This flared foundation distributed the substantial weight of the stone stack across a much larger soil area, preventing the concentrated loading that caused narrow footings to punch through soft spring ground. He set the first course of carefully selected stones in firmly packed gravel and soil, creating a stable base that would resist both settling and frost heave. The structural techniques Hans developed focused on through bonding and proper joint staggering that would maintain chimney integrity through decades of thermal expansion and ground movement. Instead of simply stacking stones in loose courses, he selected stones of varying sizes and shapes that could bridge across multiple joints in each layer. The largest stones extended completely through the 8-inch wall thickness, tying the inner and outer faces together and preventing the common failure where outer stones separated from the flue liner. Hans staggered vertical joints so that no continuous crack could develop from foundation to cap, a technique Johann Bauer had demonstrated when building the Mission chimney with its precisely fitted limestone blocks. The flue interior required specialized finishing that transformed the rough fieldstone cavity into a smooth, tapered passage that would maintain strong draft while resisting soot accumulation. Hans mixed a rich plaster of fine clay, sand, and chopped grass that he troweled over the interior stone surfaces, filling joints and rounding corners to eliminate the sharp edges where creosote typically collected. He gradually tapered the flue from roughly 10 inches by 12 inches at the bottom to 8 inches by 10 inches at the top, creating a gentle venturi that accelerated gases as they rose while preventing the swirling pockets that caused smoke rollouts. The clean-out system Hans incorporated at the chimney base provided crucial maintenance access that standard frontier chimneys completely lacked. He built a small cavity approximately 8 inches square just above the foundation level, fitted with a tight stone door held in place with iron brackets salvaged from broken wagon hardware. This clean-out allowed families to remove accumulated ash and fallen debris from the flue bottom without dismantling the firebox, preventing the blockages that caused dangerous pressure buildups and chimney fires. The clean-out door also provided inspection access to check for interior damage or animal nests that could restrict airflow. Hans created standardized measurement tools that allowed ordinary settlers to reproduce his proportions and structural details without masonry training. He planed wooden gauge sticks with permanent notches marking the critical relationships between foundation width, wall thickness, flue dimensions, and clearances to combustible materials. A specially shaped template helped neighbors establish the correct firebox back wall angle, while a simple wooden frame guided the flue taper during construction. These tools transformed complex geometric relationships into straightforward carpentry tasks that farm families could manage with basic hand tools. The fire safety clearances Hans established addressed the common problem of wood framing positioned dangerously close to hot masonry surfaces. He maintained a minimum 2-inch gap between any wooden structural member and the chimney stones, filling the space with clay and sand mixture that would not burn if subjected to extreme heat. Where floor joists passed near the chimney, Hans installed additional stone blocking that created a thermal barrier between the flue and combustible wood. He extended this safety zone to include the roof penetration, surrounding the chimney with non-combustible materials for at least 6 inches in all directions. The spring of 1847 provided a severe test of structural durability when excessive snowmelt and rain saturated the ground throughout the Minnesota River Valley. Several hastily built chimneys showed dramatic failure patterns that validated Hans's foundation approach. The Peterson cabin chimney tilted nearly 15 degrees as its shallow footing shifted in the waterlogged soil, opening a gap between the stack and cabin wall that allowed rain to pour into the interior. The Morrison family chimney separated completely at ground level during a particularly wet week, requiring complete reconstruction at the height of spring planting season when labor was desperately needed for crop establishment. Hans's deep flared footings demonstrated superior performance during the same challenging conditions. His chimney showed only minor hairline cracks in the exterior, pointing that required simple resealing with fresh clay mortar. The foundation remained plumb and solid, maintaining tight joints at all wall intersections despite the ground movement that affected neighboring structures. The clean-out door allowed Hans to remove several pounds of winter soot and debris that had accumulated over the burning season, restoring the flue to its original draft characteristics without major reconstruction work. The construction efficiency gains from Hans's standardized tools and sequences reduced building time while improving structural quality. Using his gauge sticks and templates, 2 experienced men could complete a properly founded chimney in 4 working days compared to the week or more required for trial and error construction. The systematic approach eliminated the common mistakes that forced partial rebuilds during construction, such as throat openings that proved too wide or flue dimensions that created persistent draft problems. Families could plan chimney construction with confidence in both timeline and final performance. The service life improvements became apparent as Hans's early chimneys accumulated years of operation without major maintenance requirements. Chimneys built to his structural standards typically required only minor repointing and clean-out maintenance for 10 to 15 years, compared to neighbors who faced major rebuilding projects every 5 to 7 years due to foundation failure, joint separation, or fire damage. The longer service life represented substantial savings in both materials and labor, freeing families to invest their limited resources in other essential homestead improvements. Hans documented his complete structural system using detailed drawings scratched into smooth pine boards that he shared with interested neighbors. The drawings showed foundation excavation depths, stone sizing and placement patterns, flue taper dimensions, and clean-out construction details that could be referenced during actual building. The visual guide supplemented the physical gauge sticks and templates, creating a complete instructional system that preserved the critical technical knowledge in forms that ordinary settlers could understand and apply. The structural foundation Hans established would prove essential when his complete chimney system faced its ultimate test during the catastrophic winter that would strike the region within the next decade. The winter of 1877 brought the ultimate test of Hans's integrated chimney system when a series of unprecedented blizzards struck the upper Midwest with sustained fury that isolated entire counties for months. By this time, Minnesota had achieved statehood, and Hans's techniques had spread quietly through 3 decades of neighbor-to-neighbor instruction, creating a substantial population of cabins and farmhouses built to his proportions scattered across the region. The severe weather conditions would reveal which heating systems could sustain families through extended periods. When fuel deliveries stopped completely, an emergency resupply became impossible. Railroad lines buried under 15-foot drifts cut off coal shipments to towns throughout the Minnesota River Valley, forcing both urban and rural families to depend entirely on whatever wood they had stockpiled before the storms began. Temperatures remained below 0 degrees Fahrenheit for weeks at a time, with wind chill conditions that made outdoor work lethal within minutes of exposure. The prolonged cold snap created a natural experiment comparing heating system efficiency across hundreds of households facing identical weather conditions with similar fuel constraints. The performance differences between conventional and Hans-derived chimney systems became starkly apparent as the winter progressed. Families with standard deep fireboxes and wide flues found themselves burning through their entire annual wood supply by early February, forcing dangerous cutting expeditions in life-threatening cold. The Johansen family, still using a traditional wide throat design, consumed nearly 7 cords during the extended cold period and still could not prevent their water buckets from freezing solid in the main room during the coldest nights. Their children developed persistent coughs from breathing smoke-filled air whenever wind shifts forced them to choose between suffocation and freezing. In contrast, households with Hans-patterned chimneys demonstrated remarkable fuel efficiency and interior comfort throughout the same period. Ole Larsen, who had rebuilt his farmhouse hearth using Hans's gauge sticks and templates during the 1860s, tracked his wood consumption meticulously through the severe weather. His family consumed only 4 1/2 cords during the entire winter ordeal, maintaining interior temperatures consistently above 40 degrees Fahrenheit in the main living area, while keeping secondary rooms warm enough to prevent pipe freezing and food spoilage. The structural integrity advantages became equally dramatic as the winter's repeated freeze-thaw cycles tested every chimney foundation and joint in the region. County records from the following spring documented 14 complete chimney collapses and over 40 major structural failures, requiring total rebuilding among conventional stacks. The Henriksen chimney separated completely from the house during a particularly severe January storm, filling their cabin with deadly smoke and forcing the family to shelter with neighbors for 6 weeks. 3 families lost their homes entirely to fires that started when damaged chimneys allowed sparks to reach wooden framing. Chimneys built to Hans's structural specifications weathered the extreme conditions with minimal damage. The deep, flared footings proved their worth as frost penetration exceeded 4 feet in many locations, well beyond the shallow foundations that supported most frontier chimneys. Survey teams documenting storm damage found only minor pointing failures among Hans-derived stacks, with no foundation movements or major structural separations reported. The clean-out systems allowed families to remove accumulated ice and debris that blocked poorly designed flues, maintaining adequate draft when neighbors' chimneys failed completely. The social transformation began immediately as spring revealed the stark performance differences between heating systems. Families who had dismissed Hans's methods as excessive old-world fussiness now sought out his original gauge sticks and templates, many of which had been preserved by early adopters like Ole Larsen. The Presbyterian minister in New Ulm recorded in his journal that Sunday services became informal chimney building seminars as parishioners shared measurements and construction details that had proven successful during the winter crisis. Local masons and builders experienced a fundamental shift in client demands as reconstruction began. Instead of requesting the quick, simple stacks that had dominated frontier construction, families specifically asked for narrow throat designs with smoke shelves, dedicated outside air supplies, and deep foundations. Master builder Erik Thorvaldsen noted in his account books that nearly every chimney contract signed after the hard winter specified Hans-style proportions and structural details, often accompanied by hand-drawn sketches copied from successful examples. The technical knowledge formalization occurred as county agricultural agents began documenting and distributing the chimney specifications that had proven most successful. Extension bulletins published throughout Minnesota, Wisconsin, and Iowa during the 1880s included detailed diagrams showing proper firebox geometry, throat dimensions, and foundation requirements that directly paralleled Hans's original innovations. The University of Minnesota Agricultural Station published measurement standards for chimney proportions that matched the ratios Hans had established through decades of field testing and refinement. The long-term validation extended well beyond individual household success stories as entire communities adopted Hans's integrated approach to residential heating. Towns rebuilding after winter damage incorporated his principles into building codes and construction standards, requiring specific clearances, foundation depths, and flue specifications that prevented the failures that had proved so costly during the crisis winter. Insurance companies began offering reduced premiums for homes with chimneys built to the new standards, recognizing the dramatically lower fire and structural failure rates. Modern heating system design continued to validate Hans's fundamental insights about controlled combustion air, proper draft management, and thermal mass integration. 20th century research into fireplace efficiency rediscovered the same geometric relationships Hans had established through empirical testing, confirming that shallow fireboxes with angled backs and properly sized throats delivered optimal heat output with minimal fuel consumption. Contemporary masonry heater designs incorporated thermal mass storage principles identical to those Hans had adapted from Norwegian stovecraft for frontier conditions. The chimney fire prevention techniques Hans pioneered through smooth flue finishing and accessible clean-out systems became standard features in modern construction codes. Building inspectors routinely required the same clearances to combustible materials and foundation specifications that Hans had developed to prevent the structural failures and house fires that had claimed so many frontier families. The dedicated combustion air supplies he had borrowed from indigenous lodge design and European stove practice became mandatory features in energy-efficient construction. Hans Eriksen's quiet rebellion against accepted frontier wisdom had evolved into the recognized best practice for residential heating systems across the upper Midwest and beyond. His integration of Norwegian thermal mass techniques, Dakota airflow management, German structural methods, and his own systematic observation had created a heating system that proved superior under the most demanding real-world conditions. The impossible chimney that neighbors had once dismissed as foreign fussiness became the standard by which heating efficiency, structural durability, and fire safety were measured throughout the region for generations to come.